Look at how this mechanical arm reacts to the visual stimulus. That precise movement is the result of linking two distinct frameworks: the robot operating system handling the hardware motion, and OpenCV processing the visual data in real time. By the end of this video, we will build a Python-based ROS node from scratch. This node will capture raw camera data and translate it into a format OpenCV can actually read and manipulate. Before writing any code, we need to check off the 5 prerequisites shown on this list. You need Ubuntu 20.04 or newer, the ROS Noetic framework, a Python 3 installation, the OpenCV library, and an initialized Catkin workspace. Setting up this translation pipeline is the baseline requirement for any real-time environment interaction. Without a bridge between these systems, the robot remains unable to process the visual world around it. Let's open up a fresh terminal window to begin building our system foundation. As you can see in this diagram, ROS image messages and OpenCV images use different data formats. To fix this, we install the ROS Noetic CV Bridge package, which acts as the translation block between the two streams. Moving to the terminal view, we navigate to the source directory of our Catkin workspace. From here, we execute the catkin create pkd command, adding ROSPy, sensor messages, and our newly installed CV Bridge as dependencies. Next, we open the cmakelists.txt file. Take a look at the highlighted block here. You must append CV Bridge under the Find Package Components list. Skipping this inclusion is a primary reason workspaces fail to compile. If we skip explicitly linking these system-level dependencies, any Python code we write later will remain isolated from the robot's hardware. Now that our workspace is configured, we can move into the code editor and start writing our image processing node.py script. We start by setting up our library imports. The main requirement here is pulling the cBridge class directly from the CV Bridge package we just installed. Raw sensor data routes into the image callback function, intercepting the stream. Inside, it's converted using bridge.immessage to CV2 with BGR8 encoding, translating ROS messages into an OpenCV matrix. Finally, we initialize the node, subscribe to /camera/image raw, and call rospy.spin to continuously listen for frames. This crucial block of code ensures the system maintains an active and continuous loop of translated visual data. With the code complete, let's head back to the terminal for deployment. Because of how Linux handles file permissions, we have to explicitly grant the operating system permission to execute our script. We do this by running the chod+x command on our file. Look at this split terminal setup. On the left pane, we initiate the boot sequence for the master system by running ROScore. Over on the right pane, we use the ROS_run command to execute our newly created image processing node simultaneously. Keep in mind, your node is currently listening, but it sits idle until an active camera node starts publishing data to that topic. Utilizing this multi-terminal execution architecture ensures that all disparate parts of the robot operate synchronously, allowing us to monitor the process and identify errors immediately. If your terminal is running without errors, you have successfully built a live node that translates ROS camera feeds into workable OpenCV matrices. Because the data is now in a standard matrix format, you can now apply OpenCV's optimized algorithms, like deep neural networks, directly to the video feed for tasks like face or object recognition. This data pipeline is the starting point for visual feature detection, the building blocks for complex spatial tasks like simultaneous localization and mapping, or SLAM. This same translation logic is a core component in the visual odometry modules used by autonomous vehicles and industrial drones to perceive their surroundings. Bridging the gap between the system's motion and its visual perception is a necessary step in building robots to navigate and interact with their environment.